All right. Well, these videos aren't as short as I had hoped, but I guess there's a lot of stuff in there. So at least they're under an hour so far. All right. So now we're going to talk about linkage. So this is chapter 7. Everything we talked about before involved independent assortment. And so now we're going to look at chapter 7 and talk about what happens when genes are linked together. At the beginning of chapter 7, there's a dihybrid cross that shows some goofy results. Let's see, maybe we can look at the book a little bit. And so if you look at the book, there's down here, there's a ebook. Hopefully you guys figured all this out already. And there's chapter 7, and the beginning part is talking about linked genes that do not assort independently. You know, if we look through there, the first thing it shows is what happens. So this is what we've been talking about so far. So this is what happens when the genes do assort independently. If we generate a dihybrid and then we form gametes, we can get the 4 types of gametes in equal proportion. So one thing that's important here, so this is right here, this is independent assortment is happening. You'll notice we start with big A and big B together, cross to little a and little b together, and then we get big A, little a, big B, little b. And then in the gametes, we have big A and big B together, little a and little b together. And those look like the parents up here. So big A and big B together and little a and little b together. So those are the parents. But then we also get these guys that are big A, little b, little a, little b. So these are this is a new combination of alleles. So we call this recombination. So and this is kind of what meiosis is all about. We've got big A and big B, and then we mate them with little a, little b, and we mix them together here in the F1. Then this F1 is going to redistribute them into gametes. So that's what meiosis does. It redistributes these alleles into gametes. Now, the rules of meiosis or Mendelian genetics tell us that you get either a big A or a little a. You don't get both. You don't never get 2 A's in a gamete. But if you get a big A, you can get a big B, or over here you get a big A and a little b. And you can get, if you get a little a, you can get a little b, or if you get a little a, you can get a little b. And those are equally likely. So that's independent assortment. But this new combination of alleles, even though it's independent assortment, this is called recombination. So because we're recombining the genes. Now we're going to be talking about linkage, and we're going to talk about recombination. But in linkage, recombination is due to crossing over. So we haven't talked about crossing over yet. Some of you have talked about crossing over in quizzes and stuff, but we haven't talked about crossing over. So everything up to now has been independent assortment. Now we're going to talk about crossing over. So we're going to talk about what happens when genes are linked. So the first thing they show us here, and I didn't want to show you the whole thing, but this is an example of a cross. We've got purple flowers, and the pollen is, what do they call it? Long pollen or round pollen. So it's just a dihybrid cross. So we got 2 different traits, flower color and pollen shape. We get a dihybrid where we're heterozygous for the 2 things. So it looks like purple and long are dominant. And then in the next generation, we get all the different combinations. So our parents were purple and long together and red and round together. And now we've got purple and long together. That's what we started with. Red and round. That's what we started with. And then we get some other things. So these other things are recombinants, but we do not see a 9:3 to 3:1 ratio. Without doing any chi-square or anything, just this is not 9:3 to 3:1. So we've got a bunch. Then we got 2 in the middle, and maybe these are the 3, but these are like 10 times less than 284 or more. So that's not, so if it was 9:3:3:1, the 2 in the middle here would be 3 less than, like 284 divided by 3, which is not this. And 55 is more than that. So this is just take my word for it. That is a 9 to 3 to 3 to 1 ratio. And that's really all you need to know. If we had and it's not a modified 9 to 3 to 3 to 1, we don't have time to go into that, but just it's not. So the main point here is that if you do a dihybrid cross, if the genes are assorting independently, you'll get 9 to 3 to 3 to 1, or a modification, as we saw last time. But if you don't see a 9 to 3 to 3 to 1, one possibility is because the genes are linked. So this is two different traits, two genes, but they're not showing independent assortment, so we do not get a 9 to 3 to 3 to 1. Or another way to say that is we're not seeing 9 to 3 to 3 to 1, so that means that there's not independent assortment going on. All right, so that's it. No more dihybrid crosses because this is good. So now we're going to talk about linked genes. So now with linked genes, we're going to just do test crosses because test crosses are way easier. We'll talk about the chromosomes in a minute. And I think I'll switch over to the other thing. I just wanted to show you that dihybrid cross. The other thing I want to show you about the book, though, is as you're going through here, every now and then, you will see so we'll draw out some chromosomes. So why don't you just point out, where is this? Somewhere we'll say try a problem. There's all kinds of stuff in this book. Wow, not seeing any problem. Come on. Way down here. So every now and then you'll see this. Try problem 28. So click on that, and it'll show you a problem, and then it'll show you the answer. So that's all I wanted to show you. Is that's a good way to reinforce some of these things, is to look at those problems. The other thing you can do is go down to the end here and look at assessment. And in here, there's a lot of different problems as well. So you can practice. Some of those have the answers as well. So that's a good way to practice this and practice some of these problems. So if I hadn't shown you that before, now I have. But a lot of these problems I have listed on the course web, and I've gone through the answers as well. All right, so I'm going to just switch over and do some notes. Okay, so it's really useful to look at sort of general patterns. So all of the crosses in this chapter will all look like this. We're going to always have a dihybrid, and we're going to do a test cross. And what we know from that is we should always get big A and big B together, big A and little b together, little a and big B together, and little a and little b together. So that's what the gametes look like. So this is a little b. So these are the gametes. And then if we cross them to this, we always get little a and little b from the guy on top there. Oops, sorry. And so here we've got little a, big B from here, but always, gosh darn it, but always little a and little b from here. That's all we can get from there. So little a and little b from the left, little a and little b from the top. So instead of writing out this whole genotype like this all the time, we just write this part, because the genotype of this gamete is big A, big B. And so that's that. So the phenotype, if we sort of generalized it, we would have the dominant phenotype for A and the dominant phenotype for B, which is all determined by whatever gametes we get from this parent. the gametes from this parent don't contribute to the phenotype. So we just kind of use a shorthand to ignore it. So here we would say these guys are big A, little b phenotype. These guys are little a, big B phenotype. And these guys are little a, little b. Or we can either ask about the phenotype or we can ask about the gametes. These are the gametes. Because in meiosis and crossing over and everything, we're really most interested in what kinds of gametes are formed, right? So if we have big A, if we have this, we undergo meiosis, we get these types of gametes. And we know that these are, if there's independent assortment, we get an equal amount. So this is the test for independent assortment. So we saw that if we do a dihybrid cross, we always get a 9-3-3-1 if there's independent assortment. Now we're going to get 1-to-1-to-1-to-1 if there's independent assortment. All right. So what happens if genes are linked? Well, when genes are linked, you don't get independent assortment. So what happens when genes are linked, and we do a test cross. So the good thing about this chapter is every single cross looks like this. There's one little variation that we'll throw in at the end. But, and we get, so we're going to get, what do we get? We get these kinds of things. But let's say we get, instead of, so if there's independent assortment, we'll get 25% of each because they're all equal. If they're linked, then two things are going to be inherited together more likely. Now, the classic way to do this is if we how did we get this guy here? So if we took, remember there's two ways to get to here. So let's say we did it this way. We took these guys and crossed into these guys to get this. This is our parental generation. This is the F1. And then we're doing a test cross instead of a dihybrid cross. So if there's what we call complete linkage, then these are the parent. These are the big A and the big B look like the parents, and the little a and the little b look like the parents. If there's complete linkage, we'll get 50% of each parental type. And we won't get any recombinants if there's what we call complete linkage. If we get incomplete linkage, we'll get more parentals than we will get the other ones, but we'll still get some of the other ones. So let's say 30% and 30%, that's 60%, and then 20% and 20%. So we'll get 30% parentals, 30% parentals. So you can tell which ones are the parentals by either knowing what this parental cross looked like to begin with, or by looking at which two things are the most. In this case, big A and big B and little b are the most. That makes those parentals. So we call those parentals. They're parental gametes is what they are, or parental. They look like the parents. Then these are non-parentals. Or we also call these recombinants. So anytime you do a cross, so head to net, so we have parentals and recombinants. That's what usually the words that I use. It's a little bit. I probably should say parentals and non-parentals, or recombinants and non-recombinants, but we often say parentals and recombinants. So this whole thing, this whole chapter is about figuring out what are the parentals and what are the recombinants. So let's think about that some more. So if we do a test cross, another way to think about this, we do a test cross. Now, if parentals equals recombinants, the genes are unlinked. and that means independent assortment is occurring. So if they're on different chromosomes, they're unlinked, you get independent assortment. If you get only parentals, then the genes are completely linked. And we'll talk about what that means a little bit more later. But if you get both parentals and recombinants, and the parentals are significantly greater than the recombinants, then we say that's incompletely linked. And all that means, what that means is that they're on the same chromosome, but sometimes you get crossing over between them. So there's going to be two things that we want to think about. So the first thing is we can actually use this to map the positions of genes relative to each other on the chromosome. And so that's going to be very useful. And then the other thing we'll look at is what does that look like on the chromosomes? How does crossing over, what does it look like, and how does it result in these things? But these are just sort of the first thing we'll do a cross, and so let's just do like a sort of an abstract example. So let's say we do this. We do some kind of cross, and we get, I'll rewrite it this way. And let's say we get 40% of these, and 40% of these, and 10% of these, and 10% of these. Which are the parents, and which are the parentals, and which are the recombinants? The ones that are the most, oops, can't do it that way. Sorry. So let's say it's like this. These are the most, so that's a parental, that's a parental, that's a recombinant, that's a recombinant. So that's the first thing you need to do whenever you see these crosses. Which two are the most? Those are the parentals. And which two are the least? Those are the recombinants. If they're all equal, then it's kind of hard to tell what are the parents and the recombinants. In that case, you need to know what the parental cross was. So let me just say that big A and big B together is not always the parentals, and little a and little b together is not always the parentals. But what is true is the thing that's the most is always the parentals. So the next thing we want to do is calculate what we call so the first question is, are these genes, the first question is, which are the parentals and which are the recombinants? And so first you have to identify those. Then, are the genes linked? In this case, yes. So if the parentals are greater than the recombinants, genes are linked. So yes. Then the next question is, what's the frequency? What's the recombination frequency? So in other words, what's the percentage of recombination? And that's just, you take your recombinants. So our total here is 100%, because this is in percent. So our recombination frequency in this case is 20%. So every time you'll see one of these, you're going to get these kinds of questions. Which are the parentals? Which are the recombinants? Are the genes linked or not? If they're linked, what's the recombination frequency? Another word for recombination frequency is genetic distance. We also call those map units. So in this case, the map units would equal 20. So a map unit is 1% recombination. But if you say 20%, that's fine. So let's look at a problem, or an example at least from the book. Now this is kind of a, so we'll just use this particular example. So they crossed two things, and I forget what it was exactly. I wrote down the symbols, but not. Let's go back and look at the book. We could do one of these problems, but let's go back up here. We'll draw the chromosomes in a minute. I'll talk about this in a minute. There's complete linkage. There's one of their examples. But I'm going to get down to the mapping part, which for some reason they do at the very end. So here's recombination frequency. Recombination frequency is the number of recombinant progeny over the total times 100% to give you frequency. So if you have an example where you have 15 recombinants and you add up the total offspring is 123, then the recombination frequency is 12.2%. We could try problem 15. Coupling and repulsion is annoying, but we'll come back to that in a minute. I just want to look at, they do a chi-square thing down here, which we will do. So we can test for independent assortment with chi-square. So I'm not going to use that part of the example right now. I just want to use this data for this to do map distance. So we've got 2 cockroaches, brown body with straight wings, crossed to yellow body and curved wings. And it's a little hard to tell here, but they give you the genotypes, and so this symbolism might be a little bit strange, but what this is showing here is that we're heterozygous for body color and heterozygous for wing shape. And over here, we're homozygous recessive for both. They tell you all that up in the chapter, but I just want to point this out. So this is heterozygous. It's kind of a weird symbolism with this plus, and then this is a weird symbolism over here. But then these are the numbers right here. So I'm just mostly worried about those numbers. So I just wanted to come and show you where this is coming from, and now we'll go do this little problem. And then later on, probably in a different video, we'll come back and do the chi-square thing. All right. So this was a brown straight-winged cockroach. And the symbols for brown, the gene is a Y. So the symbols they use are Y plus and Y, and CV plus and CV. So CV is curved. CV plus is wild type, which is straight. Little y, regardless of if this was a big A or a little a or whatever, you can see that we're heterozygous for those 2 genes. Then over here, we're doing a test cross. So we're homozygous recessive for both genes. So this is the same as doing this. And then they look at the offspring, and we're just looking at just look at the gametes that come from here. If you go back and look at that table, we can get these gametes together. And when we did that, we got 63. We can get yellow plus and CV. And that gave us 28. We can get yellow. So we can get this allele for this gene, and we can get CV plus. And we can get this yellow and CV together. And this is 33. This is 77. All right, so with these kinds of crosses, here's the questions. Which are the parentals and recombinants? Well, the ones that are most are the parentals. The ones that are least are the recombinants. Are the genes linked? Now, we could do a chi-square to prove this, but it's pretty dang obvious that that these numbers are not all the same, right? We don't need a chi-square to tell us that 63 is significantly different than 28. We will do the chi-square later. If it was unlinked and independent assortment, then we would expect 25% of each of these things. And so 25% of each of these is, because there's 201, is 50.25. So this is what we would expect if the genes assorted independently. So the question is, and so these 28 and 33 are, none of these things are close to 50%. So we reject this hypothesis. We'll do a chi-square next video to show how to do that. But we know that, so yes, the parentals are greater than the recombinants. So the genes are linked, yes. What's the genetic distance between these genes? Well, the recombinants are the lower ones. So 28 plus 33 over 201 is 28 plus 33 divided by 201 is 30.34%. so times 100% is 30.3%. So that's the genetic distance between these things. So what we would say is that there's the yellow gene and the CV gene, and they are 30.3 map units apart on the chromosome. So that's how we can use genetic linkage to determine how close things are on the chromosome. What does that mean? Well, that means, so you have a chromosome. And we have this yellow gene on there and this CV gene. And let's we'll just draw, well, that just means they're on the same chromosome. I won't draw the crossing over just yet. And depending on how close together they are, so if the genes are really close together, so let's say the yellow gene was here and the CV gene was here, then getting crossing over in this little region is less likely. So if you have a bunch of genes on a chromosome, so we have the A gene here, the B gene here, and the C gene here, the genetic distance here might be 10, and then the genetic distance here might be 30, that looks pretty far away, and then maybe the genetic distance here is 40. So the closer they are together, the lower this number is. And I'll talk about why in a minute. But we can use recombination frequency to make a map of how close genes are together on the chromosome. So the lower the recombination frequency, the closer the genes are together. All right, so we can use that relationship. So basically, the recombination frequency is inversely proportional to the distance on the chromosome. The higher the frequency, the farther apart. The lower the frequency, the closer together. So we can use that information to make a map of genes on a chromosome. So the first thing is to do, and so recombination frequency, so the first thing to do is to figure out the recombination percent between two genes. And that's the genetic distance between those genes all the time. Then the next thing to do is if you have a bunch of genes, you can make genetic maps. So how do we use that info to make a genetic map? So let's say we've got 3 genes. We've got the A and the B gene, and we do a cross. And so the way we figure out these numbers, then we're gonna say genetic distance, and genetic distance is in map units. And map units equals recombination frequency or percent. So A and B is 5. This is from the book. B and C is 10. And A and C is 15. So each of these numbers comes from a test cross. So for A and B, there was a cross like this. And when they looked at the gametes, they found that, so 5%, so that means 2.5% were recombinants. That's 5%. So 95%, I think it's 47.5% of these, and 25 or 2.5% of those, and you add these together, and that gives you 5. So that's how they came up with that 5. And then for B and C, they did the same kind of test cross, and they got 10% recombinants. And for A and C, they did it, and they got 15% recombinants. So once you have that information, we know that A and B are pretty close together because they're 5% apart. A and C are farther apart from each other because they're 15. And we can use these numbers to come up with a map. So we call this, when we're looking at a cross like this, we call this a 2-point cross, because we're mapping the distance between 2 points on the chromosome. Later on, you can do 3-point crosses. I don't know if we'll get to that. But no matter how you do it, map unit always means recombination percent. And so now that we have this information, we can put a map together of the relationship between these genes. So we know that A and C are 15. So the best way to do this is to take the one that's the biggest number and say, well, we know those are the farthest apart, and that's 15. And then we just have to put in B relative to these two. And A is 5 map units away from B, or B is 5 map units away from A, and 10 map units away from C. So we can make a map where B's down here, and it's 5 to A and 10 between B and C. So that's how we make those maps. So these, just in whatever numbers you get, you just take the farthest apart ones and put those on the outside, and then figure out where the middle one goes from there. They give another example, not really a problem, but just another example in the book, where they look at some other genes. So they have, this one's a little bit weird. They look at the A and D gene, the B and D gene, and the C and D gene. So they want to map these, and they've got, so there's 4 genes, 8, 13, and 23. So this one's a little bit weird, but you can do it the same way pretty much, because they've mapped all 3 relative to D. So you can take D, and you could say the farthest one away is C, because that's 23, and then A is closer, it's only 8, and then B is 13. So this distance is 13. And we'll do it like this. The D and C distance is 23. And so that makes sense. Now, they didn't do B and C. That would be useful to have that information. But what it does tell you, it's just another way of putting this map together. So this is all relative to D. C is 23 away. B is 13 away. And A is 8 away. Now, you might notice that 13 plus 8 is actually 21, not 23. And that's okay. One thing about this type of mapping is often the distances don't add up exactly, because it's not a super precise way to map things. But there's reasons for that, and we can talk about those a little bit later. But quite often, the gene that's far apart, that number is a little bit inaccurate relative to, compared to the ones that are close together. So if we really wanted to, wait a minute. Well, we still have, did I do this right? So let's see here. So D and C is 23. D and B is 13. D and A is 8. Oh, well, that's because we didn't go all the way between them. But even if we did, so this must mean that this is like 2. But later on, what we will see some examples where we might see let's say A and B, A and C, and B and C. So it might be, we might see a case where this is 20, and then this is 15, and this is 10. And so then we would expect A and C is 20. B is closer to C, so it's 10, and this is 15. So the 10 and the 15 add up to 25. But this distance only adds up to 20, and that's okay. You just have to say this is the most logical map that we can make from these particular numbers. And there's reasons for that. I'll get into that a little bit later. All right, so let's see. All right, so here's one more example of this. You can also, so we can take these individual 2-point cross examples or numbers and make maps out of them. So one more thing I want to add to this is that, so it all comes down to this. Everything is a test cross. And then what frequencies do we get out of these? And if it's 25% of each, now we don't really know what the parentals are and the recombinants in this case because everything's the same. So we know that the parentals equals the recombinants. But let's pretend that we know and that these are the parentals and these are recombinants. What this tells us is that the recombinants equals 50%. So if the recombinants, or that's also true, if the parentals equals the recombinants, then both the parentals and the recombinants are 50%. So if the recombinants are 50%, genes are linked, or genes are unlinked, I'm sorry. If the recombinants are less than 50%, significantly less, not like 49.9, but some obvious number less than 50%, then the genes are linked. Now, you might ask, what happens if the recombinants are greater than 50%? You can never get that. The maximum number that the recombinants can be is 50%. I can explain why later, but just keep that in mind. So, like if you saw some numbers, let's say you saw 20, 20, 30, and 30, and you wanted to call these the recombinants and say that the recombinants are 60%. You can't, because by definition, the thing that's the most is the parentals. So always the ones that are the most are going to be the parentals, and then the recombinants have to be the ones that are the least. And then in that case, the recombination percent would be 40%. So if the recombinant equals 50%, they're unlinked. If it's less than 50%, they're linked. All right, so that brings us to one more kind of problem. And then this is in the book too, just from the text of the book. And it gives you a set of genes like this. So now we've got a bunch of genes, and we want to figure out what we call this is, what are the linkage relationships between these genes? So what this is showing that somebody did a test cross between A and B, A and C, A and D, and calculated the recombination frequency in each case. So this is the recombination frequency, or percent. So what does that tell us? It tells us that these are unlinked unlinked, unlinked, linked, linked, linked. Because if it's less than 50%, they're linked. If it's greater than 50%, they're unlinked. So what we do then is we call these, this describes what we call the linkage relationship. So these guys are all linked together. So B, C, and D are all together in what we call a linkage group. And the other one, and A, is not linked to any of these guys. So A is kind of off by itself in its own linkage group. So we'll call this one linkage group 1. For some reason, they give it Roman numerals. And linkage group 2 is just A by itself. Then so if we want to make a map showing the relationship of all these genes, A is kind of by itself. And B, C, and D we can link together. It looks like C and D are the farthest apart. And that's 28. And then B is 20 from C and 10 from D, so B is over here. And so here's a good example where 28 and 30 don't add up exactly, but that's okay. It's close enough. All right, so I guess I'll leave it at that. So what you need to be able to do is identify parents and recombinants, determine if the genes are linked or unlinked, and calculate map distance or recombination frequency, and then construct a map. So we'll leave it there, and we'll come back next time and draw chromosomes and add a few more aspects to this. But one thing I just want to just reiterate that the easy thing about this chapter is that all crosses are the same. Everything is this. And you're going to get these 4 things potentially. And if they're all equal, the genes are unlinked. And if 2 are more than the others, then those are the parentals. The other ones are the recombinants. And you'll always see, let's say these guys are the parentals. There will always be 2 parentals and 2 recombinants. And most of the time it'll look like this. We'll come back and show some other things next time around. All right, so we'll leave it at that.